A very good morning to all of you and welcome back to a new semester. So, this particular course is titled Micro Nanoscale Energy Transport, and my name is Dr. Arvind Patamatta and I am a associate professor in the Department of Mechanical Engineering working in the area of micro nanoscale heat transfer. So, let me briefly introduce the course content that we will be talking about before we move on to the introduction part of this course. So, let me show you the overall important topics that we will be covering here. So, I have also made a time plan of how many lectures that I will be talking with each topic. So, we will have first 2 weeks we will be spending time on the introduction part. So, why do we take 2 weeks here? Because the introduction is not just a PowerPoint introduction that I will be showing in the next two or three classes. It will also involve some fundamentals which probably you need to, some fundamental terminology and fundamental understanding of some basics which you need to know before we go into the subject wise topics such as the quantum mechanics, for example, that is the next topic that we will be looking at. So, the introduction will be a little bit more elaborate here. So, we will be, for example, in fact, in the introduction we will be starting with something that we know already in the continuum scale. So, we will be looking at the aspects of macro scale heat transfer, which many of you might know or many of you are new, like conduction, convection and radiation. Okay. And we will also look at what are responsible for the modes of heat transfer on a fundamental scale, okay, their characteristics. So, all these will be covered in the introduction part, and then this will be followed by some understanding of quantum mechanics, because if you are looking at nanoscale energy transport, essentially you have to look at the duality of matter. So, either it could be a wave nature or it could be a particle nature. So, to understand the wave nature, so you have to deal with the theory of wave equation, Schrodinger's wave equation, solving the Schrodinger's wave equation for some simple systems. Okay. So, these will be dealt with in the fundamentals of quantum mechanics. So, I am not going to go into a great detail, but nevertheless we will be spending considerable time, okay, because the aspects of quantum mechanics are quite different from the classical mechanics that we understand. And so, in order to introduce you to the basics of that and apply this to a few fundamental systems will itself take about 2 weeks. So, following that, now from quantum mechanics we have to gradually move towards the statistical thermodynamics. Okay. Now, to do that we need to understand the system to which we apply the quantum mechanics. The quantum mechanics can be applied to as simple as an infinite potential well, which is like the textbook problem that we will do, to something like understanding solid state physics. Okay. Now, why I am going to talk a little bit about solid state physics is, if you are talking about nanoscale conduction, one of the simpler system is to consider solids and therefore conduction, heat conduction in solids, and therefore you have to have some background about the distribution of atoms in lattices, and therefore what is the corresponding quantum mechanical principles that can be applied to study these solid state structures. Okay. So, there are several subtopics which I have listed here. Okay. So, I am not going to go into all the details now, but we will see this, cover this one after the other. Many of you have some understanding what are conductors, insulators, semiconductors and so on, but we will give some perspectives from quantum mechanics to show you why they are classified the way that they are this way, and also some important things before we move to statistical thermodynamics. The statistical thermodynamics is basically the bridge or the interlink between the phenomena at nanoscale and the properties at the macro scale. Okay. So, properties such as heat capacity and internal energy have actually a nanoscale basis, and we can understand that through the quantum mechanics and looking at the energy states at the molecular level. But how do we directly link that to a macro scale property like temperature and heat capacity is done through the statistical thermodynamics. So, we are not interested now in looking at each and every energy state possessed by a molecule or whatever energy carrier, but finally you are looking at an statistical ensemble of these, and this is what is going to affect the properties of this system at the macro scale. And therefore, we are looking at statistical thermodynamics. Again, statistical thermodynamics itself is a separate subject being offered in some departments, but we do not have that much of time to go into all the aspects of it. We will just cover, I do not think I will have even time to cover the probability and distribution functions and so on. I think you should be able to revise it yourself, but we will talk about the derivation of some of the important distribution functions, the equilibrium distribution functions. So, which you are heard about this. So, the Fermi-Dirac distribution function, the Maxwell distribution function, the Boltzmann distribution, Bose-Einstein distribution function. So, these distribution functions are the most important fundamental distribution functions covering all the energy carriers, okay. And from there we will go on to define the macro scale properties, okay, such as the internal energy, specific heat and so on. And also we can deviate a little bit, although this is not a rigorous statistical thermodynamics, we can also use kinetic theory. See, there are two ways. One is a very rigorous derivation of all these classical constitutive relations from the nanoscale transport process, and that is what we will do, but we can also take a bypass and do a less rigorous way from what is called as kinetic theory. The kinetic theory of gases, for example, from that we can actually derive again these constitutive relations, but they are little bit hand waving and they are little bit less rigorous, but you can also do that. So, ultimately once the equilibrium distribution functions are understood from statistical thermodynamics, we then deviate and go to the non-equilibrium transport processes. So, at nanoscales, unlike the continuum scale, even the local transport process is at non-equilibrium. So, everything is at non-equilibrium. So, and therefore, how do we understand the transport phenomena happening with the local non-equilibrium is what we will study, and the particular equation to describe this is called the Boltzmann transport equation. Okay, so, I call this as BTE here. BTE is the acronym for Boltzmann transport equation, and this is the most fundamental equation for describing the transport process at non-equilibrium scale for any energy carrier. Okay, it could be electrons, it could be phonons, photons. I will come to these definitions one after the other, yeah, and or could be molecules. And we will talk about again now the rigorous derivation of the classical constitutive laws again from the Boltzmann transport equation, such as the Fourier's law, Newton's law, and here you will see that we can also do that for the electrical engineering like Ohm's law, Wiedemann-Franz law. So, at fundamental scales, the governing transport equation is the same. So, it only depends on what kind of macro scale system you are looking. If you are looking at a fluid mechanical system, you look at Newton's law, or if you are looking at a heat transfer system, Fourier's law. If you are looking at electron transport, you can derive the Ohm's law, then for metals you have the Wiedemann-Franz law and so on. So, also not only the constitutive relations, but also the macro scale transport equations, the conservation equations what we call, because we derive this for a control volume in the conservation form. Okay, you can either do it in a differential form or you can do an integral form of these conservation equations. But nevertheless, what we call as these macro scale transport equations can also be derived from the Boltzmann transport equation, and this is what we will do, and we will particularly focus on heat transfer and then show that what we understand by the continuum heat transfer need not be valid at small length and time scales. So, and if either of these conditions also does not meet, then the assumption of continuum will fail. So, it is not just small length scales, but also time scales. Okay. So, we will look at deviations from your Fourier's heat conduction equation and what can be possibly done to compensate for this non-equilibrium heat transfer process. Okay. So, this topics 1 to 5 are particularly focused on the nanoscale processes. So, you are looking at really subcontinuum level here. Now, then we will move on to continuum level, okay, but something at the scales of the microns to 1 millimeter or 2 millimeters, where you have some certain interesting phenomena happening, but they are all happening still at the continuum level. Okay. So, to study that again, we have to start with convection. So, when you talk about nanoscales, there is nothing like convection at nanoscales, it is all pure conduction, because you are talking about each and every energy carrier and there is no bulk transport at the level scale of the energy carrier itself. Okay, it is just collisions and transport of energy. So, it is primarily diffusion, and therefore, when we talk about conduction, it is at the nanoscales, but when we talk about convection, it is at the micro scales. Okay. So, you have a bulk velocity and there is a motion of the fluid and so on, and but there is certain interesting things associated with the surface forces that we will look at. So, that we classify this again whether we are looking at a single phase system or a multi-phase system. So, the single phase system, again you have to understand what happens when there is a fluid flow in a capillary tube or a micro channel compared to a classical duct flow or a macro channel, you know. So, what is the difference between these two and what kind of phenomena do you observe here. So, all this is still in single phase, but nevertheless this is different from your macro scale phenomena. For one, the influence of gravity is now reduced to a great extent, that you see several of phenomena that is associated with gravity, affected by gravity in the macro scale now disappears at the micro scale. So, following this we will also look at phase change. So, not only the single phase change here, now when I say phase change, it is also phase change due to evaporation or condensation or two phase flows. Okay. So, two phase flows could be a simple mixture of air and water, okay, and then you have different two phase patterns, and the pressure drop and these kind of things, pressure drop parameters are affected by the different flow regimes, okay, arising out of simply mixing air and water in a classical T junction, okay, and then you just look at all the flow patterns and study that. So, that is a simple two phase flow, but there can also be a state where you have purely evaporation and condensation. So, this is a classical phase change problem. So, how the phase change problem in micro and nanoscale looks, okay, and how it is different from your macro scale phase change. So, this also we will spend at least a week understanding that, and we will also briefly look at nanofluids, because although they are nanofluids, so you do not have any subcontinuum transport processes happening there, they are still in the continuum scale, but there are some important mechanisms such as slip between the nanoparticles and the base fluid, which could be at the micron nanoscales, and also certain phenomena which is different from the conventional fluids. So, what is causing the anomalous change in the thermophysical properties of nanofluids, and therefore, how they are utilized for efficient heat transport, for example. So, they are now increasingly becoming efficient fluids for better heat transfer, both in the conduction and in the convection sense. So, we will also pay some attention to nanofluids for some for a week or so, and finally, we will look at the applications. So, I am not going to cover applications while describing the fundamentals, but towards the end, because I know many of you have some idea about the applications of micro nanoscale transport. So, I will talk about some applications, maybe mostly in microfluidics and nanofluidics, and so therefore, we have about material for 15 weeks. So, I think This is basically the theme of this is how the course content has been designed. So, we see that we are covering quite a bit, we are not just focusing only on convection or conduction, but we are covering as much as possible. The breadth of the subject is quite large, and therefore, we have to see how much attention to detail we pay under each topic, and this is where the diversity of the audience come to play. If many of you have a good understanding of say quantum mechanics or statistical thermodynamics, then we could have been much faster. But what I understand is there are some of you from the BTech background, some of you are fresh from your bachelor's and you are come into the MS or PhD program. So, I do not think I can assume that you know all these to start with. So, therefore, wherever possible I will just spend enough time, but at the same time I cannot spend a lot of time teaching only quantum mechanics in this course. So, we have to also cover other topics as well. So, we will give some attention, but not too much, and then I also ask you to put your effort into going to the references and reading them. Do not just depend on only my classroom lectures for understanding the fundamentals. Okay. So, I will also point you towards some of the important textbooks. Okay. So, let me come back to the presentation here. So, let me discuss the grading pattern first. So, I would say the grading pattern has been distributed fairly between the different aspects that are required for you in order to understand an elective course. Okay. So, you have to understand that an elective course is fundamentally different. Of course, we also teach in class, we use the board or we use the PowerPoint the same way as core course is taught, but what is the difference? An elective course is supposed to be where you people have to do a lot more work than the faculty member. Okay, this is what you have to understand. So, this is the basic philosophy of offering electives. Okay. The reason is that you gain some fundamental understanding from the core courses, okay, which are taught in a classic textbook sense, line by line, you understand certain definitions, principles and so on. But then when you apply this to a more complex systems, so these are not very well structured and well defined. So, we have to do it by different ways. It is not just writing an exam that will make you understand. So, you have to do a lot of assignments, you have to do some reading on your own, you have to work on projects. So, this is where your involvement and interaction becomes more important in elective courses. Okay. So, typically we will have about 6 assignments, 6 to 7 I would say. Okay, we will see how many things we can club together. That will carry about 10% of the overall weightage, and then what I want to give will be a project that will be towards the end, but meanwhile I think you should also work on a term paper. So, it could be, I just put in bracket here, does not mean these are hard coded, could be something like you define some problems in each topic, you come out with the problem formulation and you solve them yourself. Okay. And that is a way of challenging yourself into understanding that particular topic, and these problems should not be from any of these textbooks. Okay. So, this is the condition. It could be similar, okay, do not just change the numbers and define the same problem, okay, that is not acceptable, okay, but could be on a similar structure, okay, but it is a different problem. It could be a numerical problem, it could be a conceptual problem, and you come out with the solution. So, like this, for each topic you have to, each student should take up one problem, formulate a problem and a solution. So, we have for example defined about 9 topics here, right. So, under each topic, so each student should take up one particular problem, formulate, come out with the formulation and also the solution. So, it could be a numerical problem or it could be a theoretical problem also. Okay, you understand what I am saying? Okay. So, the thing is, it will also encourage you to come out with a problem which is different from what I usually give as assignment. Okay. So, it will also make you more confident into applying what you learnt. So, this is the idea behind this particular term paper, and this will therefore be done throughout the semester. Okay. This is not only at the end of the semester, but you have to continuously do that, and as and when we cover the topics and I give you the assignment, the particular term paper concerning that assignment. So, if the assignment spans say quantum mechanics and statistical thermodynamics, so you are supposed to also complete problem formulation and solution for these two, and then hand it over to me after the assignment for that particular topic is over. Okay. So, this is a continuous process, and apart from that we will have a project. It will be basically programming, because we cannot ask you to do experiments at this particular scale. So, it could be solution of certain equations, okay, and studying certain energy transport in certain systems. We will try to do it as simple as possible, okay, for you to understand what is taught here, and we will also have exams. Okay. I mean we will have only one mid semester, which will be 20%. It looks a little bit on the lower side, but we are giving a lot of emphasis. So, 40% emphasis on the application part, okay, and the end semester will be 40%, right. So, the following are the textbooks that I will be closely following. So, one is the book by Professor Gang Chen from MIT. So, this is nanoscale energy transport and conversion. So, this came out sometime in the year 2005 to 2006. So, that was the first textbook to basically address the aspects of subcontinuum heat transport, the first textbook. So, there was one textbook before that, that is the one I have put in references number 1. So, that is by Professor Arun Majumdar at UC Berkeley, and his professor CLTN, who passed away, was the chancellor of UC Berkeley before. So, one of the pioneers who started work on microscale heat transfer, Professor CLTN. So, he was the mentor of so many illustrious people in the areas of heat transfer in the US. So, he passed away, and then Professor Arun Majumdar, he was working, and now I think he is also in a more political framework. He has taken some significant positions in the US. So, he is not per se I think doing fundamental work much nowadays. Yeah, but Professor Gang Chen is still quite active, and his students are also quite active in this area. So, therefore, this was the first textbook as far as I know, 1998 this came out, but this had everything starting from nano, micro. So, at that time there was no clear delineation of where we should stop the nanoscale transport and then continue micro. So, everything was clubbed together. So, many people were still trying to understand how only nanoscale heat transport should be taught, and that is when Professor Gang Chen in 2005 wrote a textbook only on nanoscale energy transport. So, there is absolutely no microscale in that. So, completely fundamentals. It is a very well written book, and still one of the best textbooks for this subject. And following that, I think Professor Zuomin Zhang from Georgia Tech, he also brought out another textbook on nano microscale heat transfer, but it is more or less similar in substance to the Professor Gang Chen's textbook, and still it is a very useful as a supplement. It has a lot of examples, and also solved examples, and as well as exercise problems. And there is another book which is by Professor C.B. Soban. He is from NIT Calicut, and he spent considerable amount of time working with Professor Peterson at also in the US. So, so they have written a book called Micro Nanoscale Heat Transfer, which does not have much emphasis unfortunately on the nanoscale heat transfer part. It is mostly microscale, microscale heat transfer, like flow into channels, micro channels and so on, but the fundamentals are not that extensively covered in this textbook like the textbook number 1. So, also the references if you look at microscale energy transport by Professor T. N. Majumdar, and so this is also a very good one, although there are many aspects of microscale heat transfer overlapping the nanoscale in that. There is another book by Professor Masood Kaviani from University of Michigan. So, this is called heat transfer physics. So, you see the title heat transfer physics. So, it is not written for heat transfer engineers. So, the physics part here means that there is a lot of quantum mechanics is not that much, but there is a lot of statistical thermodynamics at least. So, he has dealt with heat transfer the way it is supposed to be understood by a person with a physics background. Okay. And this also has some very interesting content, and there is another book for the microflow part, the convective heat transfer in micro channels and so on. So, that is by Professor Fagri and Sundan. Okay. The heat and fluid flow in micro scale and nanoscale structures. Okay, this is also a good book, 2004. And there is another book also that I follow, which is on micro scale flows by Professor Brian Kirby, Kirby, Brian Kirby. So, this is also a recent textbook related to microflows, and this particular textbook also has lot of applications in medical field, so in biotechnology and so on. So, it starts with very good fundamental introduction, and then slowly towards the end of the book it looks at also applications in microfluidic applications in medical field, biotechnology and so on. So, Brian Kirby is also another good textbook, and in fact Professor Brian Kirby's website Cornell has also some portions of this textbook posted online, and there are also lectures, video lectures of him talking about derivations of these equations for microfluidics and so on. Okay. So, well, these are the textbooks, and I am not very sure whether all of these are available in your library, but at least I am sure that Gangchen's book, there should be a copy or two, okay, which I had put an order request some 2-3 years back, and they had couple of copies at that time. So, you please check, and if you do not have access to these books, you let me know and we will see what we can do. Okay. But primarily you should have at least 1 or 2 textbooks and references with you, because in fact I have not given the references for quantum mechanics, statistical thermodynamics and all those here, okay, but there are many books for those. If you look at quantum mechanics, there are so many books. The one book that I usually follow is David Griffiths. So, that is a classical textbook on fundamentals of quantum mechanics. Okay. So, David Griffiths, and that is very well written, and normally any engineer should be able to follow that. And there are also many books on statistical thermodynamics. So, it does not matter, you can take up, for example, thermodynamics of materials. So, if you look at thermodynamics that is taught to material scientists and metallurgy, lot of statistical thermodynamics are covered in that. Okay. So, any textbook which deals with thermodynamics of material should have a reasonable portion of statistical thermodynamics. All right. So, these are the major textbooks that I have listed here, but you should supplement these with the particular textbooks for quantum mechanics, statistical thermodynamics and so on. Okay. So, all of these books does not cover these in a great detail, okay, but if you want to understand the basics, you have to go back to the corresponding textbooks. So far, any questions on the overall structure? So, I have given you a very big picture, I think, on this particular course. I think what you typically need on the very first day, okay, and now you have to decide whether your expectations are being met in this particular course or not. Okay. So, the emphasis will be mostly on the fundamentals. So, fundamental understanding to get a clearer picture, I hope. Unfortunately, it is also very mathematical. So, I will try to see if I can reduce the mathematical aspects a little, compress them a little bit this time, because the very first time I taught, I myself realized the students found it very mathematical, and therefore, they were sometimes lost in the equations to understand the clearer picture. So, this time I will try to compress that, and I will also try to bring out the physics as much as possible. Okay. So, if you have any questions, then we can talk about that. We do not have much time, but I will just stop with this quote. This is the starting point of every textbook on related to nanoscale energy transport. This was the famous quotation by Professor Richard Feynman in his lecture at the American Physical Society held at Caltech in 1959. So, there is plenty of room at the bottom. So, yeah, I mean this is quoted for everything pretty much related to micro nanoscale, need not be heat transfer, it could be something else. So, physicists also quote this, nowadays engineers are also starting to quote this, but nevertheless means that we are now seriously dealing with systems which are much below the scales of what our our physical senses can resolve. Okay, and therefore, we have to understand, even though we cannot see this kind of phenomena with our observation with our physical senses, we should be able to see how we can capture them in whatever possible way we have understood this so far. Okay, does not mean that whatever we have understood is complete, there is still a lot of room, people still are struggling to understand phenomena at these scales, but nevertheless some picture has emerged, and let us try to at least understand part of that in this course. And our emphasis will be primarily on energy transport. So, the energy transport here means it could be say fluid flow in the convection sense, or it could be heat transfer in the conduction sense. Okay. So, this is our primary emphasis. For people who are working in electrical engineering, the energy transport could be flow of current and things like that. So, but as people from mechanical sciences, our emphasis should be on these two aspects. Okay. So, with this I will stop here, and tomorrow we will get into a more detailed introduction on the subject. Okay. Thank you.